Hi, I'm Sean. I'm a H1 maths student and I'm studying maths in college. And I'm here to help you get through your Leaving Cert maths questions. So let's get into it. Okay, so here's our question. We're asked to differentiate 1/3 x squared minus x plus 3 from first principles with respect to x. So the keyword obviously being first principles. There's a certain way of doing this, and we're always going to be using the same formula, so I'm going to write that out. So in the case of differentiating from first principles, what we're going to be looking for is always the limit of f of x plus h minus f of x all over h, where h approaches 0. So just to give you a visual representation of what this is and sort of an insight into actually why we're doing this formula for differentiation. So as I'm sure you all know, when you're differentiating, what you're actually trying to do is find the slope at a particular point on the curve or line that you're dealing with. And we find it for any general point x. So let's just choose this point up here. We're going to call that x, and we're just going to zoom in on that. So here we have what x would look like if you zoomed in far enough, sort of roughly. If you went extremely close to the line we're dealing with, this is what it would look like. But of course you can't talk about a slope without having 2 points, because a slope is the change in vertical distance over horizontal distance between 2 different points. So we're just going to define another point up here where this is x plus h, and h is the distance horizontally between these two things. So that's the bottom half of this triangle here. And the vertical distance on the y-axis is going to be the difference between f of x plus h minus f of x, because we know that f of x is just the y-coordinate with respect to any x-coordinate. So now the vertical distance between the 2 points is f of x plus h minus f of x. And naturally, as you reduce the value of h, we're just going to get closer and closer to the value of the slope at x. So basically, the closer h gets to 0, the more accurate our derivative or our slope is. And so that's what we're trying to figure out in this formula for differentiation from first principles. So basically the slope as h approaches 0. So that's just a brief overview. Of course, there's plenty of ways to find out more detailed information on this online and in many books. So if you're interested in really understanding it, then I recommend looking into it a little bit. But the first thing we're going to do as far as solving the question goes is just sub in where we have x in the question for x plus h to find f of x plus h first. So therefore we have f of x plus h here. And we're just going to expand out our brackets and try to simplify this as much as possible. So once we expand everything out into singular terms, we're just going to have this whole line here involving x terms, h terms, and the constant 3. Of course, we also have just regular f of x, which is 1/3, and that should be x squared there, minus x plus 3. So to find f of x plus h minus f of x, we're just going to take away all of these x terms away from what we just figured out. So just to save you some time, I can tell you that whenever you're doing this correctly, what you're going to get is just that you have only terms involving h left, so you lose anything involving x or any constant. So what we're left with in this case is just 2/3 xh plus 1/3 h squared minus h, which are all our terms involving h up here. So now we're just going to divide all of this by h in order to get what we want to get, which is something we can find the limit of as h approaches 0. So when we divide across by h, we're just going to have to drop the h here. This is just going to become 1/3 h. And we have minus a h, so to divide that by h, we're just going to get 1, so that's going to turn into a 1. So finally, the limit of all this as h approaches 0 is just going to be equal to 2/3 x, which doesn't change. Our 1/3 h is going to go to 0, so we're going to leave that out. Minus 1, which obviously won't change either. So that means our derivative is equal to 2/3 x minus 1. And feel free to check it using the regular method of differentiation of bringing down your exponent and all that if you want to from the original function. But this is the final answer. And for getting all that out, you are going to get 20 marks. So pretty much all the marks of the question are going for this part A. Definitely worth revising. So in part P, we're given these two functions, f of x, which is equal to ln 3x squared plus 2, and g of x, which is equal to x plus 5. We're asked to find the value of the derivative of f of g of x at x is equal to 1/4, and to give our answer correct to 3 decimal places. Okay, so the name of this here, where we're getting a function of another function, is called composite functions. And the biggest mistake people make is that they try to just multiply them or something like that, and that's going to get you nowhere. It even says in the marking scheme that that's worth no marks. So the way to actually do this is wherever you have x in your first outside function, which is f in this case, So we have an x squared here. We're going to plug in everything that's in g of x, which is x plus 5. And then we will have f of g of x, which is what we're looking for. And then after that, we're going to worry about a differentiation. So here, where we have 3x squared, we're just going to sub in 3 times x plus 5 all to be squared. And that's all we've got to look out for, because the rest is just plus 2. So this is f of g of x. And although you don't have to technically simplify this any further, I'm just going to multiply out this bracket to get rid of that as well, just to make things a bit easier for differentiating. So the expansion of x plus 5 all to be squared is equal to x squared plus 10x plus 25. And we're just going to multiply in our 3 now. So we're left with 3x squared plus 30x, and we have 3 times 25, which is 75, and plus 2 is going to be plus 77 at the end. So that's as simple as we're going to make f of g of x. The next step is to use the chain rule for differentiating composite functions. So here we have in our log tables the exact formula we're looking for. We have u of v of x, which we can just obviously change to f and g. So our dy dx is going to be equal to du dv times dv dx. So that is our chain rule in general. So we have y is equal to f of g of x, of course, and our u is f of x, and our v is going to be g of x. So before we start differentiating, I'm just going to let f of g of x be equal to y from here on, just because it's going to look a little bit nicer, but you can definitely use f of g of x throughout if you wish. So now to actually tackle the derivative itself, first of all, we've got to differentiate the natural log function. So here back in your log tables again, we can see that the derivative of ln x is going to be 1 over x. So that's what we're going to be dealing with as well. So we have 1 over whatever's inside the bracket, which of course for us is not x, but it's 3x squared plus 30x plus 77. So we have that. But because we've also got a function which is more complicated than x inside the bracket, we've got to differentiate all of this and then multiply that by what we already have, I should say. So that's our 1 over x. But because we've got something inside the bracket, which is 3x squared plus 30x plus 77, which is more complicated than x, we've got to differentiate everything inside the bracket and then multiply it on at the end. And this is kind of confusing because in our log tables we know that if we have y is equal to ln of x, dy dx is just going to be equal to 1 over x. But what they're actually doing here is they're differentiating the x sort of silently because the derivative of x is 1. So they could write it as 1 over x times 1, where 1 is x differentiated, but obviously that's kind of pointless because it doesn't look really great and it doesn't really serve any purpose. But just keep in mind that whenever we're differentiating ln of x, we're actually also differentiating x itself as well, even if you usually can't see it. So the derivative of 3x squared is going to be 6x, and the derivative of 30x is going to be 30. So we now have that as well. So the last step now is just going to be to plug in for x is equal to a quarter, which is the value we're looking for. So the value of our derivative at a quarter, we can just find by subbing in a quarter, obviously, where we had x. And this big fraction here, I think is best done on a calculator. So when you plug all that in and press equals, you're just going to get 504 over 1,355, which as a decimal is going to be equal to 0.3719, which corrected 2 decimal places is 0.372. And that is our final answer. So definitely good practice for using composite functions there. One last thing to watch out for is if they ever use the notation f circle g. That is essentially the same as saying f of g of x. So it's the same thing, but I just think this circle can lead you to maybe think of it as a product, so I try to stay away from that. But that may appear in the mark scheme as well. But that's it for part B, and for that you're going to get 5 marks. So of course a very top heavy question here, and that's it for today's video. I hope you enjoyed it. If you did, there's going to be other similar videos in the description, as well as some other helpful resources, and I'll see you next time.